student coming to take a test at 4, so when he gets here, I'll start the test for him and give you guys a chance to catch up on your notes. Okay, so here goes. We proved this direction last time, right? The forward direction last time. So let's begin with the converse direction. Suppose P of x is irreducible, all right? And then suppose I is an ideal of polynomials over F such that the ideal generated by P of x is contained in I, which is then contained in polynomials over F. All right. Now, we already know that, what do we know? We know from a previous work, we already know that the polynomials over F are a principal ideal domain. Right? That's something we proved. Meaning that every ideal in the polynomials is generated by some element.
What was our definition of irreducibility?
Irreducible means that if you factor it, one of the factors has to be a unit.
Oh, okay. So kind of like.
It doesn't have a non-trivial reduction, is the way I say it.
But we're talking about polynomials over a field, right?
Yeah, but that definition of irreducibility applies to numbers just the same.
Okay.
So since it's a PID, there exists g of x, right? A polynomial such that what? Such that I is generated by g of x, because every ideal is principal. Every ideal can be generated by a particular element, right? Okay, so then what? Well, then notice, observe, whatever word you want to use. I'll use note. It's less right. P of x is equal to P of x times 1, right? So that means it's an element. So this is like a general step made in a lot of these proofs. Is like if you have the ideal generated by an element, the fact that that element is an element of that ideal often is part of the argument. Here it is for this one. And so this is a subset of what? Subset of this one, right?
Oh yeah, ideal. Okay, yeah,
It's a subset of that. And what does that mean? So therefore, there exists polynomial k of x, right? Such that what? Such that how can I say this? P of x is equal to k of x times g of x, right? So, hence, the degree of k of x is equal to 0, or the degree of g of x must be equal to 0. Why is that? Because either, at least one of those has to be a unit. And the units are constant polynomials, right? Non-zero constant polynomials. So, at least, well, not at least, one of these has to be, well, yeah, fine. I think you can say just one of them is a unit, because I assume P of x is irreducible. And by assumption, if it's irreducible, it's not a unit. All right. If I recall correctly, I think that was a presupposition of irreducibility, is not a unit, a non-zero non-unit. Now, I might be remembering that wrong. I should probably look up, but I'm not 100% sure that irreducible can't be a unit. I'm forgetting at the moment. Yeah, not a unit. So irreducible can't be a unit. Okay, so what does this mean? If the equal to like some constant times g of x, right? And then it follows then that the ideal
What's a scalar?
generated by p of x is equal to the ideal generated by c of x. So these are equal. In other words, this is equal to I, right? On the other hand, if the degree g of x is equal to 0, then that means that g of x is equal to a non-zero constant, right? And you can prove that the ideal generated by a non-zero constant is equal to the whole thing. See, because you know, if you look at like f of x is equal to the constant times 1 over the constant times f of x. So you can obtain any polynomial as a non-zero multiple of a constant. So like if you have a constant and your ideal, if you're a constant's a unit, so if you have a unit and you're generating an ideal with a unit, you end up getting the whole ring again. Oftentimes we see this as like, yeah, if you have the ideal generated by 1, you get the whole ring R. We're dealing with ring R. But anyway, so that's it. So that proves maximality. See, because either we have the ideal in between p of x and the whole thing is p of x again, the ideal generated by p of x,
P of x
or
is the ideal.
or that this is equal to f of x, and that's what we need for this to be a maximal ideal. Is there's no ideal properly contained between the whole ring and that ideal, so it's maximal. Okay. So that completes the proof of this one. All right. And this is a very, very nice result because it gives us the following corollary, right? Which is corollary 4.6.22 in my notes, which says this, p of x irreducible implies f of x over the ideal, the factor ring is a field. So again, this is assuming the setup of the previous theorem already. I just don't want to write it all out again. What's the proof? Proof is just this. If it's irreducible, then that implies that the ideal generated by p of x is maximal. But we have previously proved that if you take a ring, mod and maximal ideal, you get a field. So, corollary 4.6.23 says f of field, and then p of x, a of x, b of x, polynomials over the field, right? If p of x is irreducible over f, right? And p of x divides the product of a of x times b of x. All right, then p of x divides a of x, or p of x divides b of x. Let's look at the proof of this one. It's corollary. The proof's a little bit longer for this one. So let's look at it. Suppose p of x irreducible over field f. All right. Then, of course, we have p of x is maximal. this ideal is maximal, right? Hence, the ideal generated by P of X is likewise prime, right? Because maximal ideal implies prime ideal. Okay. And you know, if you want further evidence of that, notice that, you know, by the previous corollary, f of x mod p of x is what? Is field, right? Which is also integral domain, right? A field is an integral domain with extra structure. So the fact that that quotient is an integral domain, remember, we had before proved that that's an integral domain if and only if the ideal which you're modding by is a prime ideal. Okay? So this is a prime ideal. If a of x and b of x are polynomials, and p of x divides their product, what's that mean? Then we of course have a of x, b of x equal to what? Like k of x times what? Times p of x, right? Some multiple of p of x has to be equal to the product of a and b if that's the case. So what's that mean? This is an element of what?
Well, isn't P of X prime?
Yeah, well, p of x, the ideal generated by p of x is prime.
Oh, okay. Well, that's inside of the generation of P of X, right?
Right. So we have the product of two things is inside a prime ideal, right? So by definition of prime ideal, that implies either a of x is in the ideal generated by p of x, right? Or b of x is in the ideal generated by p of x. So we've got a few different definitions floating around here. We have prime ideal, we have maximal ideal, we have irreducible element, we have unit, and so I don't think we've defined prime element yet. I'm trying to remember if we've done that already. I don't think we've done that yet. No, we've only defined irreducible polynomial. We haven't just defined prime at this point, in this part of the course. I mean, we might have before, but okay, anyway, the point is what? This means a of x is equal to, like, you know, g of x times p of x, right? And this means b of x is equal to, like, you know, h of x times p of x, whatever. There's some, right? And what does that say?
They're both in the idea.
Right, well, this one says that a of x is a factor, excuse me, what does it say? No, it doesn't say that. This says that p of x divides a of x, right? And this one over here says that p of x divides b of x, which is what we set out to prove. Then p of x divides a of x, or p of x divides b of x. So. All right. I said, in the notes I say, this theorem is important in the proof that polynomials over Z form a unique factorization domain. In particular, the uniqueness stems from this theorem. I don't think we're actually going to go over the detailed proof of that anyway, so it's kind of a side comment. Okay, so I want to show you guys some maybe notation here. So I think I try to encourage this notation in the homework, but it's not quite present in the notes. So what's a good notation for working with these, you know, factor rings if you want to actually do calculations in them? So I'm going to try to look at example 4.6.24. So here we're asked to look at z2 of x mod the ideal generated by x cubed plus x plus 1. Now this is cubic, right? So we can test the irreducibility of this p of x, right? Doing what? Looking for zeros. And that's kind of easy here because we're over what?
Mod 2.
Mod 2. So you got two things to check, right? P of 0, 1. P of 1, 1 plus 1 plus 1, right? Also 1. Therefore, no zeros, consequently, can't be reduced. It doesn't have a linear factor. This is an irreducible cubic. Are there any irreducible cubics over real numbers?
I think we have a formula.
There is no irreducible cubic over the real numbers by the intermediate value theorem. Every cubic has to cut through the x-axis somewhere. So you can always factor out a linear factor from a cubic. There's no such thing as an irreducible cubic over the reals, but this is over z2, so things are different.
Oh, that makes sense because we have the one.
Right.
It's not. It's not a cube. There's not a square.
Right. And so the story is over other fields like you're less familiar with, like rational numbers or z mod, whatever. You can have irreducible polynomials of arbitrary high degree. You can find a rational polynomial of like stupidly high degree, which is irreducible. All right. So anyway, my point is this is an irreducible polynomial. Therefore, this thing is a field, right? And essentially, the point is this: if you think about this, that means that you can reduce down. Essentially, you have the relation that let's see here. How can I say this? X cubed plus the ideal generated by p of x, right, is equal to minus x minus 1 plus this ideal. Right. Another way to say it is you can think of x cubed plus x minus 1 as being 0, in z2 of x mod. But this is a bit of a, this notation isn't very good, right? I mean, so there's a way around this, which is just to say, okay, I'm going to let alpha equal to x plus the ideal generated by x cubed plus x plus 1, just to change notation a bit. And if you think about f of x plus the ideal generated by x cubed plus x plus 1, and just think about it for a bit, you realize that I can reduce x cubed to x, x minus 1. So anything higher order than x cubed, I can just contract back down to either constant or x squared. So an arbitrary thing here looks like this. It looks like a plus bx plus cx squared plus this ideal, right? But the thing is, with this notation alpha, right, you can absorb this and just rewrite this as a plus b alpha plus c alpha squared. Just a sleight of hand here. Now I don't have to write the ideal explicitly, and I also have things like, where alpha cubed is equal to 1 minus alpha, among other things. And so this is a field with how many elements? No.
If we're talking about Z2 too, is that what you're talking about?
So Z2, that's right, you get two choices for Z2. So how many choices you got here? You got A, B, C.
So 6, like combinations.
Mm-hmm.
Wouldn't that be like 6 or something?
Well, how many, if you think about a 3-digit number, how many possibilities do you got? Those range 10 to things, right? It's like 1,000, right?
A 3-digit number?
Yeah.
That can like also be like numbers.
It can go from 0 to 999, right?
Alright, I'm a little lost, sorry.
So So what I'm trying to get at here is this can go from like 0, and then you've got 1, you've got alpha, you've got 1 plus alpha.
Oh, alpha's a choice of.
Well, this is, you know, so ABC, you can do 0, 0, 0, 1, 0, 0.
0, 1, 0.
0, 1, 0, 1, 1.
Okay,
I'm not putting these in any particularly good order at the moment, my bad. I mean,
No, I get what you're saying.
there's 8 choices. So there's 8, you know, 8 elements to think about here. 1 plus alpha.
So yeah, do like 3 combo 4, 4 combo 3, something like that.
Then you get like, you get 1 plus alpha squared. I'm not putting these in any particularly good order at the moment. You know, you got just alpha squared alone. You've got alpha plus alpha squared, right? 1, 2, 3, 4, 5, 6, 7. I'm missing 1. What am I missing?
You have just alpha, 0 and alpha?
Just alpha.
Well, 0 and alpha wouldn't make sense.
0 plus alpha is still alpha.
Yeah, alpha squared plus 1, don't forget that. 1, no.
Alpha squared plus alpha squared.
Oh, I know what it is. I'm missing this one, which is 1 plus alpha squared. So there you go. Those are your 8 field elements. I know this is a field because this is a polynomial mod and irreducible ideal. The ideal generated by an irreducible, rather, which is a maximal ideal, hence this is field. And you can work out the multiplication table for this field if you wanted to. Like, how do these multiply? Here, I'll just do a sample one. I don't want to do all of them. But if we did like 1 plus alpha, right, times 1 plus alpha squared, how would that multiply? Well, just the usual rules. You know, I get 1 plus alpha squared plus alpha cubed. Aha, alpha cubed can be reduced. See, I trade my alpha cubed for the defining relation. Right here, right? So I trade in my alpha cubed for a, you know, 1 minus alpha. I should have written that last, my bad. Anyway, plus 1 plus alpha squared plus alpha. So these guys cancel, and you get 2. Well, the 1 plus 1 is 0. Basically, this piece and this piece cancel. You're just left with alpha squared, right? So an interesting question to ask is like, what's the inverse of any particular element in here, you know? Because this is allegedly a field, right? So there's got to be an inverse amongst these choices for every one of these non-zero. I mean, 1 is inverse is 1, great. What's the inverse of alpha squared? Or what's the inverse of, what's the inverse of alpha squared? Can we figure that out? Well, check this out. So, alpha cubed, there's something to mind here. Alpha cubed plus alpha equals to 1, right? So let me forego this annoying question of what's the inverse of alpha squared. That would have been a good homework question to ask you. Maybe it still is, but I think I already wrote all your homework, so I'm kind of out of luck. So I guess I just have to put that on the final. Wait, what? No. Idle threats. Let's see here. So alpha times alpha squared plus 1, right? Equals to 1. What does this say? See, because I can factor like that, right? And then you learn, aha, the inverse of alpha, right? Alpha inverse apparently here is alpha squared plus 1. And likewise, alpha squared plus 1 inverse is alpha.
Can I, when you said where alpha cubed is equal to 1 minus alpha,
Yeah.
how do we know that?
That is what is set up here. This is alpha cubed equals to, oh man,
Yeah.
did I miss a minus? I think
looking for a minute, I was just like, I don't know, I couldn't figure it out.
You get the point if you don't wanna fix it.
Yeah, I don't want to fix it, but I do want to fix it. So what I should have said is alpha cubed equals to minus alpha minus 1, right? That's what that means. Because the thing is, this right here, right, is equal to minus x plus p of x, right? Plus minus 1 plus p of x by the definition of cosine addition. And so this is literally, and you can pull the minus out, and then that's minus alpha, and
Pull them out, so.
and this is likewise pull the minus out, and you get minus 1. So I mean, that's the. But you're right. I should have had.
I just figured if I didn't know how to set that up.
Let me go ahead and fix it. This should be. I'll do the fixing in red. And all right, so I should have had a minus here, and that would have basically down here, instead of having that, I would have this, right? And the funny thing is, it doesn't change anything.
That's what I was
It doesn't
thinking.
at all?
No, yeah, that's what I was thinking, like
That's
when
funny.
you changed
It
it.
doesn't change anything.
I was just wondering, cause like,
That is-
if I wasn't gonna set one up, I didn't know how you pulled that.
That's funny. Of course, then, but I should really have, this is minus 1, right? So I should have a minus and minus alpha down here, right? And, but, how to say this? Oh, here's the funny thing. Multiply this equation by minus 1, what do you get?
Alpha cubed,
Alpha cubed
alpha.
plus alpha equals to minus 1, right? And here's the perverse thing about Z2. Minus 1 is 1. So we're good. There are not many examples where you can make this many mistakes and not really need corrections. But anyway, the larger point here is, if you're working in a field where you define the, you're looking at a field where you're quotienting by some polynomial, then here, I'll show you another one briefly here. If I can find out how about this. So like example 2, just to kind of drive the point home here. If I take the real polynomials, right, and I quotient by x squared plus 1, which is irreducible, right, then I can look at this as the set of a plus b alpha, such that, alpha is equal to x plus the ideal generated by x squared plus 1. And a and b are real numbers, right? And here, in this case, alpha squared plus 1 is going to equal to 0. So something kind of cool, and anytime that you're like defining polynomial, anytime you're defining a polynomial has like a 1 sitting in it, that gives you a way to find the inverse of the element that you're adjoining here. So another way to think about this is, well, we'll talk more about this as the lecture goes on here, but another way to think about this is we're taking the reals and we're sticking on another element alpha. Really adjoining this element alpha to the reals. It's a new number, it wasn't there before, and it's such that its square plus 1 is equal to 0, right? You could look at it as that. And so what's the inverse of alpha? Well, by construction, this new fangled space we're building has alpha squared plus 1 equal to 0, right?
Is this just I?
It is just I, but let's look at it. So 1 is equal to minus alpha squared, right? Which is alpha times minus alpha. Therefore, alpha inverse is equal to minus alpha. Indeed, of course, you're familiar with the fact that, I times minus so therefore 1 over I is equal to minus I. The multiplicative inverse of the imaginary unit is, but anyway, my point is just that if you have a defining polynomial, and you have a 1 in it, you can find the inverse of the element you're joining pretty easily like this. So, by the way, the example 24, we took polynomials over what? Characteristic 2, Z2, and we modded by a cubic. We ended up with the constant, the linear, the quadratic degrees of freedom, like unbound. So that gave us 2 to the third. That's a field with 8 elements. One of your homework questions is to construct a field with 27 elements. So what you'd want to do there is look at like polynomials over Z3 and find an irreducible cubic. See if you could take Z3x and mod by an irreducible cubic. That would give you a field that has A, B, and C free to range over 0, 1, and 2 in Z3, which then in turn would have 27 elements. So like that's, in that problem, I don't actually expect you to list all 27 of the elements. I just want you to construct the field and give arguments for why it is a field and why it has what it has. All right. The remaining theorem in this is just that if you have a polynomial with integer coefficients, you can factor it into a product of non-unit polynomials that are constant times a product of irreducible polynomials of positive degree. So basically, there is a unique, up to the ordering of the factors, factoring of a polynomial over with integer coefficients. I don't even want to write it down. I don't have a proof to show you. It's just something I want you to be aware of. That brings us to lecture 27. All right, so I think I will continue writing some things out, but at some point I'm going to go to the projector probably today. So we're not quite there yet. I mean, it's good to see all the proofs, but I don't think I need to write them all out because they do have sort of the same flow at some point. So once you've seen a few of them, you can kind of piece together where we're going with later ones. But this we should all write down because it's important. Definition. Let D be an integral domain, which means what? It's a commutative ring with unity. No zero divisors. Yeah, very good. Let A and B be elements of this domain. All right. Numero uno. A and B are associates. All right. If there exists unit U in D such that B is equal to AU. This is what it means for them to be associates. 2. A is an irreducible. All right. If A is not a unit, and whenever A is equal to CD, then C or D is a unit. In other words, an irreducible is an element which does not permit a non-trivial factorization, right? You cannot factor into a product of elements where both of the factors in your product are non-units. 3, A with A not equal to 0, all right, is prime and A divides BC implies A divides B or A divides C. Now, I think that if we really kind of take a look at this, it doesn't seem like, this doesn't really quite square with our usual definition of prime for integers. What's your usual definition of prime for an integer?
Not divisible besides by 1 in itself.
Right, it's only divisible by 1 in itself, because we think about positive divisors.
Yeah, yeah, I'm seeing this now.
So actually, that's irreducible. That definition we usually give, that's the irreducible definition for prime. Whereas this right here we call Euclid's lemma for integers. Right? So just a warning, the abstract meaning of these terms is a little bit at odds with your more familiar usage in Z, but these are the standard definitions.
3 is the one I'm stuck on.
So this is like Euclid's lemma. If a prime divides a product of integers, then either the prime divides one or the other. We called it Euclid's lemma, I believe.
Okay. I thought you were saying it's prime if and only if that Euclid's lemma holds.
Well, yeah, this is the definition of prime. So this is if and only if. I mean, I could add another F here in each case. I mean, these are definitions. But, now, it turns out that prime and irreducible are interchangeable in many common contexts. We'll see that, but they're not always. That's my next example. Before I get to the next example, a good example of associates. So, how about this? We can write 5 and like -5 are associates in Z, since 5 is equal to -1 times -5, and that's a unit, right? So numbers and their negatives are associates in Z. That's kind of all you got to work with in the integers, because you only got the unit either 1 or -1. Okay, but in Gaussian integers, what did we learn? So plus or minus 1, plus or minus I units in the Gaussian integers, right? So if I start with 3 plus 2I, that has associates what? You can do like -3, -2I, or I times 3 plus 2I, or -I times 3 plus 2I. These are other associates of 3 plus 2I. So the more units you got in your ring, the more associates you got. So, how about a field? Think about a field for a second. What are associates in a field? If C not equal to 0 is in field F, right? Let B be in the field, right? Prove to me that B and C are associates. Well, B not equal to 0.
Yeah. They're associates. All numbers. No.
So my question is, B is equal to blank times C. You can put a unit there.
No, B and C are equal. Over field.
Well, I mean, in the field, I can do B times C inverse, right?
Yeah.
Because if C is non-zero, its inverse exists in the field, and B times C inverse gives you back B again. So any two non-zero elements of a field are associates. in contrast, Gaussian integers, you got 4 associates. It's associated to itself as well, right? I mean, of course. And 2 is, pairs. The associates are pairs for integers. All right, enough about this. I was trying to make sure that the definition of associate is not, doesn't just flow past you like, It's easy to write a definition down, but to really understand a definition, we need examples, right? And we need counterexamples to add contrast, right? And we to best understand, this example is helpful, right? Example 4.7.2. So here we have, we're going to look at z adjoining the square root of -3, right? And so there's some redundancy in the course here because we've already done these things before. So I'm going to try to not redo everything in here. Okay? But of course this is z adjoining the square root of -3. And, okay, so I say we can study 1 plus the square root of -3, right? This is clearly an element of this ring, right? By the way, is z adjoining the square root of -3 an integral domain? Well, it is, all right, no. I'll just tell you it is. There's no zero divisors in this thing. I don't know if I've actually proved that or not, but we could. Of course, we have the norm to work with, right? If we want to. But, let's see here. So if we look at this, 1 plus the square root of -3, right? Times 1 minus the square root of -3, what's that equal to? 1 minus 3, right?
So minus 2.
Well, 1 minus a -3 rather. I've lost a minus here. So not 2, but 4, right? Which, by the way, is 2 times 2, right? Thus, I point out that 1 plus the square root of -3 divides 2 times 2, right? Yet, you can argue that 1 plus the square root of -3 does not divide 2. To prove that 1 plus the square root of 3, oh wait, you're fine. So you guys prove that while I'm setting up this test. Yeah, the other room. I'll let you go to the other room. You're not listening either. Yeah, you can have calculator. So the proof here is just like, suppose there was, and you'll find that you can't solve the equations essentially. So what would it mean if there was? If 1 plus root square root of -3 divided 2, what would that mean?
There's just a plus.
Yeah, a plus b root 3.
Yeah.
So we'd have 1 plus square root of -3 times a plus b square root of -3 equals to 2, right? If that was the case, what does that give you? That gives you
1 plus a.
yeah, a minus 3b, right? Plus b plus a square root of -3 equal to 2. Now we have proved before that we can equate coefficients of these kinds of equations, right? So this tells us a couple different things, right? From this equation, we got 2 equations, 2 integer fancy equations there. So on the one hand, we have a minus 3b is equal to 2, but on the other hand, we have the b plus a is equal to 0. Well, that's nice, because then apparently minus b is equal to what? A, right? So equation number 1 gives us what? Gives us a minus minus 3 times minus a equals to 2, otherwise known as 4a equals to 2, otherwise known as a equals to a half. Uh-oh, that's not an integer. Game over. Okay, so the solution we're looking for is not allowed. So 1 plus, so what does this tell us then? What does this say about 1 plus root 3? Square root minus 3. Notice we have, what's the definition of prime? Whenever a divides b times c,
Or a times c.
either, yeah, right, if a divides b times c, either a divides b or a divides c. In this case, both b and c are both 2, and we can't divide either of them, right? So this shows 1 plus the square root of minus 3 is not prime, right? It's not prime. But is it irreducible? Is it irreducible? So to prove it's irreducible, the arguments involve the norm.
Yeah, I was about to say, because 2 has a norm.
Right, so to prove it's
I
irreducible,
think it's 1 minus root 3, or minus.
oh yeah, what's the norm here?
For 2 is 1 minus root 3.
So the norm of a plus, sorry, it's hard, okay. What do you say?
Oh, for that, 3ba squared, something like that.
Yeah, so a squared plus 3b squared is what it is. So that's the norm in this context. And I stated in some generality in the notes, all right?
Mm-hmm.
But there it is, that's the norm.
Yeah, because Pell's equation, right?
Well, this one's not by Pell's equations, this one's just the,
Oh, it's not minus, yeah.
anyway, the point here is, if, it is true this though, we have this, the norm of like alpha beta is norm alpha, norm beta, so, you know, the properties you proved for the norm before, they're still, and it's been like a month and a half since we've been doing them, but they're still true. So, go figure. But if, let's think about it this way, if 1 plus the square root of minus 3 was equal to alpha beta, right, that's the question, we need to prove that necessarily alpha or beta is a unit. And so if you take the norm, we've got the norm of 1 plus the square root of minus 3 is norm alpha and norm beta, right? By the multiplicativity of the norm. But what is the norm of 1 plus root 3? Well, it's 4, right? So we have 4 is equal to n alpha and beta. So the only way, if both alpha and beta are not units, by the way, theorem, n of alpha equals to 1 if and only if alpha unit. That theorem, still true. So if alpha and beta are both non-units, that means, and we got that they're a product of integers, n of alpha, n of beta, we are forced to a 2, yeah.
Which means alpha and beta are norms are equal.
Right, so if, and then let's get into the details, if alpha is equal to like, you know, a plus b squared minus 3, then we have a squared plus 3b squared equals to 2. But that equation has no solutions, no integer solutions. To figure that out, just try cases. See, because we definitely can't have b to be non-zero, because then we've got 3, which is bigger than 2, and there's nothing we can do about it, because a and b are integers, right?
We don't have a minus sign.
So our only choices really are like 1 plus or minus 1 and 0 here, but those don't work because 1's not equal to 2. And then you get to 2, plus or minus 2 here, we got 4, you can't do it. So therefore, no such alpha and beta exist, which then proves that if you have a factorization of 1 plus root minus 3, it necessarily contains a unit, right? So therefore, therefore, 1 plus the square root of minus 3 is irreducible because we tried to find a non-trivial factorization of it and we failed. We cannot reduce it. So as you can see from this example, there is a distinction between prime and irreducible in this context. Okay? Let me get out my handy dandy notes here. Come on. What? Oh, there it is. So we are in lecture 27. If I turn off the light, you're not going to go to sleep, are you?
No.
Okay. You seem pretty awake today. So
I am pretty awake today.
if I see any evidence of sleepiness, I will immediately order you to drop and
Alright.
give me 2 plus 3 eye push-ups.
Oh Lord.
Too complex for you?
Don't make that joke. That's not funny.
Don't make that joke. It's not funny.
Come on, let's be real.
Let's be real. Oh. It's horrible. Did you find my hair?
It's definitely not rational.
No.
You go open up Pandora's box and she'll know that.
Let's see here. So can you guys? Oh. Questions out there. You guys can see the questions. Whether the camera can see it, isn't it? Start blathering about these notes for. There we go.
Line system.
All right, so we get to where we were. So we've just proved that we have examples of things that are irreducible but not prime, right? At this point in the notes, I introduced the norm that we talked about before. A little bit different because I add absolute value to it. The next thing here, like norm of a plus b root d is the absolute value of a squared minus db squared. So that covers the positive and negative d cases, all right? We spent a lot of time with like negative d, so it's just a squared plus db squared. We don't need the absolute value. But if you're working in like the Pell's equation case, you don't want to put absolute value there. Anyway, so this example 4.47 is formidable. So, I mean, you can look at it, but proving irreducibility is not always as easy as the example we just did. And so, like example 4.77 is kind of the next level boss up the down. If you go down the labyrinth and you start looking for other fights, this is the next one around the corner. It involves like a few more steps, and it's kind of a pain. Here we go. And in an integral domain, every prime is irreducible. In an integral domain, every prime is irreducible. So, let me see if I can find my laser. I really want a laser. All right, so in an integral domain, every prime is irreducible. So let's look at the proof here. Suppose A is a prime in an integral domain. If A is equal to xy, then what? A divides x or A divides y? Definition of prime, right? If A divides x, that means x is equal to AB for some b. Thus, x is equal to, well, x times 1 is x, of course, which is AB, which is, let's see here, how did I get, oh, A is equal to xy, right? So put the A equals to xy there, which is x times 1b. So what's that mean? Oh, and then how am I getting from here to here? Integral domain, cancellation property, right? Not that the inverse exists, mind you, but we have the cancellation property nonetheless. So I can say 1 is equal to yb, right? And so that means that y is a unit. And, so we just took an arbitrary factorization of A, right? And we proved that one of the factors has to be a unit. That proves that A is irreducible, because if you have a factoring of it, it has to have a unit in the factoring, right? So, and well, that's half of the argument, right? If A divides y, then a similar argument doesn't for y. Okay, so that's good to know. What does this say about z adjoining the square root of -3 then? If prime, I guess it doesn't say anything, right? Because we had not prime. What does it say? Does it say anything about when things aren't prime?
That is divisible.
I mean, what would the...
It is divisible, and one of the things aren't, and both of them don't have, one of them isn't forced to be a unit.
Well, I guess what I'm saying is, this says prime, in the context of an integral domain, prime implies irreducible, right?
Mm-hmm.
Does that say anything about when it's not a prime?
Actually, reducible.
I don't think this theorem says anything directly about when it's not a prime, right? But it does say this, right? If you're an integral domain and you find something's not irreducible, then you can justly conclude by logic
It's prime.
it's not prime. Because if it was prime,